everyone. Today we are going to see harmonic functions. A real valued function of two variables x and y is said to be harmonic if second order partial derivatives exist and they are continuous and it should satisfy Laplace equation. So I have given here Laplace equation in Cartesian form because the function is a function of x and y. So it should satisfy the Laplace equation uxx plus uyy equal to 0. Then we can say the function u as is a harmonic function. So if suppose u is in polar form, then the second order partial derivatives exist and it should be continuous and it should satisfy Laplace equation in polar form. So that Laplace equation in polar form is u r plus 1 by r ur plus 1 by r square u theta theta equal to 0. This is the Laplace equation in polar form. So if the function is in polar coordinates, then if the function is supposed to be harmonic, it should satisfy the Laplace equation in polar form. Next we are going to see conjugate harmonic function. If u plus iv is an analytic function, that is f of z equal to u plus iv is an analytic function, then v is called as the conjugate harmonic function of u, or otherwise u is called as the conjugate harmonic function of v, or u and v are called conjugate harmonic function. So one for one, the another is the conjugate harmonic function. So next we are going to see the properties of analytic function. First property, the real and imaginary parts of an analytic function f of z equal to u plus iv satisfies the Laplace equation. So real and imaginary part means u and v. U is the real part and v is the imaginary part of the analytic function f of z. So given this f of z is analytic, we need to prove that u and v satisfies the Laplace equation. So otherwise the same property can be specified as real part u and imaginary part v of an analytic function are harmonic functions. This property can be stated like this also. So now what is given? F of z is analytic given. So using that statement we are going to prove that real and imaginary part satisfies the Laplace equation. So given f of z equal to u plus iv is an analytic function, what we know about this statement is the first order partial derivatives should exist and it should be continuous and it should satisfy CR equation. So if a function is analytic means we know this sufficient condition, it should satisfy Laplace equation. These are the two Laplace equations. So that is named as equation 1 and 2. So now I need to prove, first I am taking u, I need to prove it satisfies Laplace equation. So I need to prove that uxx plus uyy equal to 0. I need to prove this, to prove that. So I am taking this first equation I am having ux. So I need to get uxx means I need to partially differentiate this equation 1 with respect to x again. Then similarly, second equation I am having uy here. So if I differentiate with respect to y again, I will get uyy from this equation. So from first equation I will get uxx, from second equation I will get uyy. Then I will check whether adding these two I am getting 0. If I am getting 0, I can say that It satisfies Laplace equation, hence it is harmonic function. So see here that equation 1 is partially differentiated with respect to x. So equation 1 is ux is equal to vy. Ux equal to vy is the first equation. So it is differentiated with respect to x partially. So we are getting uxx is equal to vyx. Then take the second equation uy equal to minus vx. This is the second equation. This is partially differentiated with respect to y. So uyy equal to minus vxy. Then these two equations we need to add. So you will get uxx plus uyy in the left hand side. Right hand side vyx minus vxy. So vyx is equal to vxy if v is a continuous function. So both are same. If the order changes also, it will give the same value. So therefore if you subtract it, that is equal to 0. So it says that uxx plus uyy equal to 0. So u satisfies the Laplace equation, hence u is a harmonic function. Similarly, I need to prove for v. So if I want to prove that v is the imaginary part of the analytic function f of z. So then again I need to go back to equation 1, this equation. So I need to partially differentiate this equation with respect to y to get vyy. Then take this equation number 2. I need to differentiate with respect to x to get vxx. Then adding these two, I need to check whether it is equal to 0. So in that way, if I do it, I am getting vxx, vyy equal to 0. So I can say that v is satisfies Laplace equation. V is a harmonic function. So I proved that real and imaginary part of an analytic function f of z are harmonic functions. But the converse of the above result need not be true. So if u and v are harmonic function means it's not necessary that the function should be analytic. So converse need not be true. Then next we are going to see similar property in terms of polar coordinates, polar form. So here same real and imaginary part of an analytic function u and v. U is expressed in terms of r and theta and v is expressed in terms of r and theta. So it should satisfy the Laplace equation in polar form. So similar way, we need to take the given statement, that is the function is analytic. So if the function is analytic means we know it satisfies CR equation. So we need to take here CR equation in polar form. CR equation in polar form is UR equal to 1 by R v theta and VR equal to minus 1 by R u theta. So taking these two equations, we need to differentiate partially with respect to R, with respect to theta to get the required terms, and then simplifying we need to check whether it is equal to 0. So if it is equal to 0, I can say that it satisfies the Laplace equation, hence they are harmonic function. So this you can easily try.